Hi everybody, in this video I'm going to go over Apex Section 7.3.3 study, which goes over the ideal gas law. This is the part 1 video, so there's going to be a part 2 video tomorrow. Alright, let's get started. So, the first concept we need to understand is absolute zero. So we always know that molecules are in motion. If it gets so cold that all molecules stop moving, that is called absolute zero. That is a very, very cold temperature, and it's so cold that scientists have never actually seen it before. But there is an idea that there is this very, very cold temperature where all molecules stop moving. Since this would be such a low temperature, there's a different temperature scale that scientists use, and it's called the Kelvin Scale. So you've seen Fahrenheit and Celsius as different scales of temperature. There's actually a third one called the Kelvin scale. And it's based on this idea that 0 degrees Kelvin would be equal to absolute zero. So that means there's never a negative Kelvin. Okay. Kelvin is abbreviated with a K. There's no degrees sign. And how it's defined is Kelvin is equal to degrees Celsius plus 273. So let's say absolute zero is 0 Kelvin. What is it in Celsius? Okay, if we want to get Celsius by itself, we'd have to subtract 273 minus 273. So in degrees Celsius, absolute zero is negative 273. Okay. We can also do these conversions with bigger numbers. So let's say 15 degrees Celsius. Okay, that's the temperature, it could be outside. What is that in Kelvin? So we would say K equals 15 degrees Celsius plus 273. And we would end up getting 288 Kelvin. So it's pretty simple to convert them. You just take your Celsius and you add 273. Or if you have Kelvin, you just take your Kelvin and subtract 273 to get Celsius. Okay? So we've talked about in the previous section how the properties of gases depend on each other. We can actually use all these properties that we talked about last time to put it into one equation. And this is called the ideal gas equation. And the ideal gas equation says pressure times volume equals moles times R times T. Let's look at each of these separately. So P is pressure, the pressure of the gas, and it's measured in atmospheres. V is the volume of the gas. It's measured in liters. N is the number of moles of gas. T is the temperature of gas. And we're going to measure that temperature in Kelvin. So we're going to start using that Kelvin right away. And then R is a constant. It's always the same for all gases. It's called the gas constant. And it's equal to 0.0821 liter atmospheres per mole Kelvin. Okay, that's kind of a long unit. But the gas constant R for any gas, any temperature, whatever, it's always 0.0821. And this allows us to make calculations if you have one of these things missing. Now, in order to use this equation, you need to assume your gas is ideal. So ideal means like this imaginary perfect gas. Now, it doesn't exist in real life. We're just pretending that this imaginary perfect gas exists. And if it was a perfect gas or an ideal gas, then the particles would take up negligible volume. That means in their container, they're like really, really tiny in comparison to the size of the container. And the second assumption is for a gas to be ideal, the gases need to not interact with each other, right? So we said there's these intermolecular forces like in solids and liquids, and gas, there's mostly not intermolecular forces. So this assumes there's none at all. So these assumptions are not ever 100% true. They're just assumptions of an ideal or imaginary perfect gas. But if you have high temperature and low pressure, you can get pretty close to this. So then we can use these equations as a very good estimate. Okay, so let's practice doing that. All right, let's say over here, the volume of a gas is 1 liter, there are 5 moles of gas, and the temperature is 300 Kelvin. What is the pressure? So this here is our volume, this is our moles, this is our temperature, and we're looking for pressure. Okay, so let's put in our equation, PV equals nRT. We don't know P, we know volume is 1 liter, N is 5 moles, R, we said, is always that 0.0821, always, that's what R is. And T is 300 Kelvin. Make sure you're using Kelvin. If you were given Celsius, you'd have to add that 273 to get it into Kelvin before you could use this equation. So let's start solving it. So if we put 5 times 0.0821 times 300 in our calculator, we're going to get 123.15. So we have 1 times P equals 123.15. To get P by itself, you divide by that 1. And you have pressure equals 123.15 atmospheres. Okay? And that would be our final answer. So we just took our equation, we plugged in our numbers, and simplified. Let's try one more. We have 2 moles of a gas have a pressure of 2 atmospheres. What is the volume at 400 Kelvin? So 2 moles, so we have N equals 2. And we have a pressure of 2 atmospheres, so P equals 2 atm. And the temperature is 400 Kelvin, and we're looking for the volume. So let's put in our equation. Our pressure is 2 atmospheres. We don't know the volume. N is 2 moles, times R is 0.0821. Always, remember that's our gas constant, and our temperature is 400 Kelvin. So let's try and solve this. First, we're going to start on the right, put this in our calculator. 2 times 0.0821 times 400 gives you 65.68. So we have 2V equals 65.68 divided by 2, right? We want to get that V by itself. And you end up with V equals 32.8 liters. Remember, the unit for volume is liters. And that would be our final answer. Okay, so from this section of the apex, what we really want to know is, what is this absolute zero? What is the Kelvin scale? How do you convert Celsius to Kelvin? What is this ideal gas equation? We need to know these 2 assumptions, that the particles take up negligible volume, they're very small, and they don't interact with each other. And then we need to be able to use that PV equals nRT ideal gas equation. And here are a couple examples. Okay, so this is just part 1. Come back tomorrow to watch the part 2 video from this section. Thank you.